kind of get this party started. So happy Thursday. I said Tuesday earlier. So happy Thursday. A few weeks left, as we'll see on the next announcement screen. Glad you all made it. And today we begin Unit 14. We're going to go through 2 lessons in this unit, specifically seeing how we can translate our knowledge of the unit circle to another coordinate plane through a wave-like motion, what we're going to call sinusoidal graphs. And effectively, we'll talk about that in depth today and then continue that next week. Here's our big announcement. Same thing as I mentioned on Tuesday. RLA, RLQs, keep using them. Keep working on the assignments and the ed puzzles. Keep in mind, I mentioned on Tuesday, if you weren't here or missed in the beginning, open date to turn in assignments and ed puzzles, meaning if you missed the due dates, I know some stuff was due on Tuesday, you haven't completed it, don't worry, I'm focused on you getting it done rather than it being on time or late. So really there is a flexible late period, and that flexibility is through the rest of the year. So just kind of get those assignments done. Maybe I'll see you tomorrow at 11 if you have any questions during the office hour Zoom session. And T-4 weeks has never been more real because we are now in our last official class of the 4th week left. So not what we're doing today. That was what we did on Tuesday. It was Unit 6. Today we are transitioning into Lesson 8, which is where we're going to talk about that unit circle basically unhinged. And we'll see that a unit circle can be viewed in terms of vertical displacement, center, and horizontal displacement. I guess distance away from the center, which we'll call co-height, and that's just side-to-side movement on the coordinate plane. So basically this entire unit that we're going to focus on, and that's 2 lessons, in lessons 8 and 9, specifically starting with today, is taking that idea of the unit circle and now applying it to trigonometry and motion, aka the distance away from things. All right, let's get it started here. So we're going to start off in Lesson 8, which is on page 118. I know y'all don't have the book, but if you've seen those PDF copies that I posted, this is what we're on. And I want to first off kind of revisit the behemoth unit circle that we've seen over the last weeks. And here in the unit circle, we saw that we could measure circular movement in 3 ways: angular movement, degrees. We also saw that we can measure distance around the circle in terms of radians, these pi's, and that's again just the pieces of the crust, so to speak, or the pieces of the circumference. And then last but not least, we zoomed in, and I'm focusing on my first quadrant, these specific reference angles that we've alluded to over the course of this unit. We also mentioned that we can talk about the location of any given spot, which is really what we're going to focus on today, based on how far it took horizontally to get to that spot. And let me use a different color here, how far it took vertically to get to that exact spot. So we're going to look at these ordered pairs effectively today from the context of a Ferris wheel. So like the car of a Ferris wheel, the X tells you how far it is away from the center, and the Y tells you how far away it is vertically from the center. And that's really what we're going to focus on today. So just kind of a reiteration, a repetition of that unit circle concept from the last couple of weeks. So on page 118, what we're going to do here now is take the context of a Ferris wheel. So here's the situation that we have, and then we're going to basically try to figure out the height of any given car on the Ferris wheel from our knowledge of the unit circle. So right off the bat, we know that a Ferris wheel has a radius of 10 meters. And you can kind of see that, and let me kind of highlight this maybe a little bit more in depth here. Ferris wheel has a radius of 10 meters. We can see that on the circle down here, the distance from the center up to a car at any given point, which is all these points on the unit circle, or the coordinate plane, excuse me, combining the 2 words. All of those little dots are basically cars on the Ferris wheel, thus the radius is 10 meters, and it's really easily seen across the x-axis from legitimately 0, 10. Okay, so we have a 10 meter or approximately like 33-foot radius of a Ferris wheel, and we want to measure the height of the passenger car that starts in the 3 o'clock position, which I have highlighted in green right down here at the bottom of our screen right now. So basically when it starts on the x-axis. So then we basically know if it's starting on the x-axis, it's starting, we'll just call it at a height of 0 meters to make this kind of more efficient and easy to use the unit circle to our advantage. So here's what we know. We know that the radius is 10 meters, Keep in mind that on the unit circle, we said that the radius was always 1 unit. So in this case, we're going to do a little bit of conversions here, and we're going to say, all right, let me make this writing a little bit bigger. We're going to call one given unit. 1 unit is equivalent or equal to 10 meters. So 1 unit in relation to this Ferris wheel is exactly 10 meters, and we'll keep that in mind for our calculations as we look for vertical movement or height of these cars. So effectively, all we need to do, and I say all, and it sounds kind of crazy, is fill out this huge box here, which is just a function table, and then we can use that to graph a function on the next page. But I started off by saying all we need to do is fill out this box, and I boxed the whole thing. And I know I'm saying the word box a lot, but I kind of highlighted this whole table originally. But we know now through our use of reference angles that really all I need to do is find the first quadrant, and then I can use that information to copy and paste the next 3. So really I want to focus my attention on just these first 5 angles at 0, 30, 45, 60, and 90, and then we'll use our knowledge of repetition or equivalency to help us solve that. So right from the jump, they give us one of them, and that's at a 0-degree rotation, before the Ferris wheels even started to move. If we started here, well then naturally we have moved 0 meters in height. Now the question is, after a 30-degree rotation, let me get this little blue writing off here. After a 30-degree rotation, we're now up, and we are at this spot here as a car. The question that they're now asking is the following. What's your height? So we can use our knowledge of the unit circle to our advantage here, because we know that the unit circle at a 30-degree rotation, through our knowledge of sine and cosine, really SOHCAHTOA and 30, 60, 90 right triangles, is the following ordered pair. √3/2, 1/2, which means, let me make my pen a little bit smaller here. Sorry about that. I'm trying to jump between too big and too small. If I know from the unit circle that at a 30-degree location that I'm at a horizontal movement of √3/2 and a vertical movement of 1/2, well, I can use this to my advantage now to figure out what the height is in terms of an actual understandable thing, not just a fraction 1/2. So I know my radius is 10 meters. That's our basic unit there that we just described. And I know that my y value, what we're really looking for, because that's all I care about, is the y value, is just going to be 1/2 of that. So effectively what that means is the height at a 30-degree movement on a 10-meter radius would be 1/2 of 10, which is equal to 5. Okay, flashback to the unit circle again. Now we're not focusing on a 30-degree movement, but we're focusing on a 40-degree movement. Sorry, 45. So here's our 45-degree movement. The car continues to move up and up and up. That would be the radian measure, but again, we are focused on the height, so I want to figure out that right there. So what is the height in meters? Well, again, my radius is always 10 meters in this context. I flash back to my unit circle, which says the location of any given point at a 45-degree angle was √2/2. And again, I'm not really flipping back and forth between the unit circle consistently right now, so we could, and I'll do this one more time. I'm just going to kind of show you where I got this from. Right there, there's my location of horizontal movement and vertical movement relative to the radius at 45 degrees, that unit ordered pair right there, boom. Okay, so I know that basically what we're looking for, which is the height in meters at this point, the y right there, is just going to be the y value at 45, √2/2, but we know now that our radius isn't 1 anymore, our radius is 10 meters, so we take √2/2 and we multiply it by 10, and I believe we get approximately 7.1, which I'll verify in just one second, my calculator. And we can continue to repeat this process, and I'm going to 2 more times, and then we'll just basically copy and paste so we don't have to fill out 30 of these things. So last one, now I've succeeded in finding my 30-degree, my 45-degree. Let's transition now to a 60-degree movement. So now we have gone from our starting point here we have moved all the way up and around at 60 degrees, leaving us to right there. Okay, so we still know our radius is still that single unit of measure, 10 meters. And now flash back to the unit circle, which feel free to reference at any given time. That would be our ordered pair. So now all we have to do is reference, all right, we're looking for the y value, which on a 60-degree movement is √3/2. Our radius is 10, and then we can multiply that out. So I'm going to actually reference a calculator now to get some exact answers here. So I actually have a screenshot of this for our advantage. 10 to the 1/2 was equal to 5. 10 times √2/2 was equal to about 7.1. And the one that we're now looking at, 10 times √3/2, is about 8.7. So I'm going to just copy that down right up here. Now again, just in the context of what we're actually doing here, all of these numbers, 5, 7.1, and 8.7, are basically telling us the following: that on a 10-meter radius Ferris wheel, if you went 30 degrees up, if you went basically a 12th around the circle, you would be 5 meters from your starting point. Let me move this over to the left, actually, boom. If you were up at a 45-degree, you would be 7.1 meters above the ground or where you started at. And last but not least, if you were up at a 60-degree, you would be effectively 8.7 meters higher than when you started. Now the last one, the 90-degree angle, is the easiest one to figure out because guess what? We know our radius is 10 meters. 1/4 of your way around the circle. You've gone from start to 90 degrees. You've gone pi over 2 radians, but we're asking just for the vertical height, which literally is just the radius here of 10 meters. Therefore, a 90-degree angle is just the radius itself. You're 10 meters tall at that point. Okay, now to finish this off real quick, we don't need to go through and do this process a bunch more times because here's why. Effectively, once we know a 60-degree, I'm just going to draw a vertical line, we know the 120-degree angle. So all I'm going to do is I'm going to figure out what was my value at 60 degrees, 8.7, and copy it down to 120. Sorry, I'm supposed to be an eraser. Once we know our 45-degree, look at that, right across from it, literally the same exact heights, the same y values, opposite sides on the x, one's positive x and negative x, but the heights are the same. They haven't gone up or down relative to each other. Therefore, if I know a 45-degree angle, height, boom, 7.1, I know the 135. And hopefully you're kind of seeing this process. Therefore, across from the 30 is 150. So if you know 30-degree angle, which we do, it's the same as the 150 at 5 meters. If we know the 0-degree angle, and we did, that was at a height of 0, it's got to be 180. Now, same exact situation, just now all of our heights are going to be negative because take a look here. We have a 30-degree angle from 180 to 210. Our reference angle is 30 degrees. Therefore, whatever our height was at 30 degrees, 5, is just now how far we are beneath the starting point, which means basically we're just dropping down that same height that we got at 30 degrees, 5 meters. And now since we're dropping down, we're going to call it -5. And the same process, notice as I'm now just filling in all of the negative heights. 45 relates to 225, 60 relates to 240. And again, the reason for that is because this 240-degree angle right here is really just a 60-degree angle in the opposite direction. Well then, 270 would relate to 90. So now we're just 10 meters down, the radius in the opposite direction. And then it's a little copy and paste game as we continue this off. At 240, you're at the same height as 300. So at 240, same height as 300. 225 is 315. So 315, all I'm going to do is literally just take what I got at 225 and paste it on down. And last but not least, 330 was at the same exact height as 210. So you get the idea, 210 is at -5 right there. So really what I did here is now the main reason of this, although I went through a lot of just kind of like, hey, copy and paste, the main thing I really wanted to focus on was the first few terms, specifically the 30, 45, and 60-degree angles, and then using our ordered pairs to our advantage here with our radius of 10 units, and then figuring out, oh, well, if a 30-degree angle has an ordered pair of root 3 over 2 comma 1/2, if I'm looking specifically for the height, the y, which we know is height on the coordinate plane, I just take 1/2 of that radius. If my 45-degree angle was root 2 over 2 comma root 2 over 2, again, if I'm looking for my height, my y value, I just take that root 2 over 2 and relate it to my singular unit of measurement, 10 meters, and I get that multiplication outcome, the product, to be my height displacement. So really the whole point of this lesson and next lesson is to realize that all of that work that we did on the unit circle over the last few weeks, seemingly weird and cryptic at that point, and when we look at the unit circle as a standalone value, it is weird because it's just like a circle with a bunch of numbers on it. But once we can see that a lot of things in life are secular or circular, meaning they come back around, kind of a lot of ideas and different ways of saying that in terms of recycling and seasons and motion and just wheels, which you can see in a lot of facets of life, circles. Basically, we can now apply basic trigonometric math outcomes that we got through some basic math, some geometry, and then apply it to real world situations like this kind of silly example of a Ferris wheel to get actual understandable data like, oh, how high am I above where I started in any given point? And that's kind of now where lesson 8 builds off of all of those previous concepts. So what we're going to do as we are still kind of working through is now we're going to finish off this lesson today by doing number 4, just right beneath it. And I'm going to basically need to screenshot all of the work that we just did here to make lesson 4 more easy and understandable, so that way I don't have to just keep jumping back and forth. So sorry as I erase this stuff, just screenshot it. Sweet, okay. And now what I'm going to do is I'm going to sketch a graph of number 4 from that function table that we just created. So let me crop this out here real quick. I'm sorry about the delay. Should have had this preset and ready for us before class, so my apologies. All right, that should be fine. Oh my gosh, okay. So here we go. It's almost done. Now what I'm doing here, everyone, and the reason why it's taking so long is I'm trying to make this big so we can see it, is we have this function table here on the right that are basically ordered pairs, okay? What I mean by that is that's an ordered pair 0, 0. Here's an ordered pair 30 degrees, 5 meters. Kind of get the idea, hopefully 45 degrees, 7.1 meters. So what we're really seeing now is basically, and I'm going to kind of make this smaller here, the ability to unhinge the circle. And what I mean by that is, real quick, I'm going to take myself off the major screen sharing application that I have here so you can't see my iPad anymore. All right. And basically, this is a unit circle, okay? It's obviously a bad circle, but hopefully you can see my screen. I have a shoelace, okay? Unit circle just talks about something rotating around. Now I used a shoelace as a unit circle because all I have to do is untie it real quick, and then the circle can unhinge into a line. Like take a water bottle, undo the adhesive around the label, you can straighten that water bottle label out into a flat piece of paper, right? So basically if you have a circle, it's not the best circle because it's really long, I only have 2 hands, but you could take apart at any part of the circle and flatten it out and have a line. So what we're going to do there effectively is we're now going to apply that logic to the ordered pair or the coordinate plane that we see on page 119. But bear with me as I try to connect my iPad back. It's always a little bit better to kind of explain this in person than it is over Zoom, but we know what we're working with. So sweet, okay. I'm back in 2, 1, cool. So now we're back. Basically, the whole point of that visual was to say, all right, we're going to take this circle and graph it in a different way. And I'm going to use these points right here to my advantage to do so. So at the point 0, at the starting point, we had a point of 0, 0. Here we go. Here it is graphed. 0 over, 0 up. So you notice that my degrees of rotation is my x-axis, and my height in meters is my y-axis. Okay, next one up. 30 degrees, 5 meters. So I'm going to go over to 30 degrees and up to 5. And I'm going to do this much quicker now. Ready? 45 and 7.1. Maybe right about there. My next point is going to be at 60 and 8.7. And my last is at 90 and 10. Okay, now we start to see things coming back down our way. At 120, we're at 8.7. So at 120, 8.7. 135, 7.1. 150, 5. And at 180, where am I getting this from? 180, we're back at 0. Boom, 180, we're back at 0. And if we start to connect these dots, already we're going to see this wave-like motion. Now, as I cut this out, we're at 210, we were at -5, and basically we start to work our way down from those values to look a little something like such. And then at 270, we were at -10, and we start to see these points connect into what is our major sine form. Remember, we're talking about height sines of a graph. So basically what this is going on here, with this multi-curve situation, is if we took this circle and I cut it, snipped it right here. That's really bad scissors, but I snipped it right there. Starting point at a height of 0, 0. You can kind of see the circle manifest in a weird way. It basically took that circle, cut it, laid it on a straight line, and then let the natural flow of our heights of the actual thing, basically taking this up that way, not down that way, for a visual perspective on what just happened. But long story short, all of these points that we just got were obtained from the unit circle, the ordered pairs, with a radius of 10 meters, multiplying all of those measurements for the y at any given angle, the y value at 30 degrees, 1/2, y value at 45 degrees, root 2 over 2, and y value of 60 degrees, root 3 over 2, all times our radius of 10, which gave us our heights that we then graphed on the Ferris wheel circle, the coordinate plane about the Ferris wheel. Sorry, my brain obviously is not working at a high level right there when I'm trying to speak. That is the main idea that we're trying to get to over the course of this next 2 lessons, is we can take a unit circle, apply it to any given measurement, 10 meters for this example, and then graph it in a way that's potentially more easy for us as math students and readers of any graphs, easier for us to understand, oh, this obviously was going up until it reached a max point, and then you started to trend back down closer to the earth, back to where you started, and then you were below your original starting height until you got back up. A lot more functional and understandable graph at that point. And that's actually where we're going to end it for today, y'all. Didn't get to the homework, which is totally okay, because as a matter of fact, next week, next Thursday specifically, we're going to have a dedicated lesson where we try to get through any and all assignments, lesson 8 and 9 specifically. So we're going to stop it here so as not to overload our brains with crazy new material from unit circle to coordinate plane function solving. But that is effectively the meat of today's lesson. So if you have any questions, please let me know. If not, I will maybe see you tomorrow during the office hours at 11. If not, I'll see you on Tuesday. So have a great weekend. Have any questions, stick around. If everyone else, take off.
Thank you.
Thank you. I appreciate y'all being here. Thank you, Alan.